Welcome back, everybody. Hope everyone's doing okay. The only thing I have announcement is I won't be here next week, right? Okay, we got spring break next week, so what we'll do is finish up chapter 9 and then maybe touch a little bit on chapter 10, so we get a little head start on the chapters. Keep in mind when you come back, there will be exam number 3, which deals with chapters 7, 8, and 9. Okay. All right. So, any questions at this point? Comments?
Really quick, I'm sorry, I missed that first part of what you said. Did you say we have a midterm or no?
You will have an exam number 3 when you come back from spring break.
Great.
Which would be chapters 7, 8, and 9.
Thank you.
Yeah, no problem. Okay. Any other questions? Okay. Well, let us continue with the chapter 9 and finish that up. And we ended up on this slide right here. Let's back it up. We had talked about pH and so forth, and the effects of too much acid material on your teeth. So anyway, now we get into what's called the solubility rules. Now, with respect to solubility, we're dealing with ionic compounds only, metal, non-metal combinations, okay? And we're dealing with aqueous solutions with respect to solubility. Now, we'll go over the rules, and you're going to end up with either being able to classify the ionic compound as either soluble or insoluble. Now, when we talk about it being soluble, we essentially basically say it's 100% soluble, totally goes in solution. Classic example would be table salt. You can make a salt solution, a teaspoon of salt, maybe a quart of water, and that sodium chloride will go totally in solution, okay? Or you could get something like magnesium hydroxide, which based on the table says it's insoluble. Now, what that means is, well, let me go back. When it says soluble, that means that's a strong electrolyte. The electrolytes, I'm sure you're familiar with that term. There's a lot of drinks out there that they say electrolytes, you got to keep up with your electrolytes. Well, electrolytes are nothing more than the ions that you ingest. If you're working out a lot, you're sweating a lot, you are losing a lot of ions, and those ions are necessary for your body to conduct electricity, to communicate with point A of your body to point B. Without those ions, you have muscles don't communicate very well, but they're nothing more than atoms that have lost or gained electrons. So hence sodium chloride plus charge and sodium chloride negative charge, and they conduct electricity. When they're soluble, 100% dissolved, strong electrolytes, okay? When it's classified as insoluble, that does not mean that it's totally 100% insoluble. That just means that maybe 1 to 5% is soluble. A little bit is in solution. So those ions are in solution, but a very small quantity. The bulk of the material is still intact. And most of the time, they are a precipitate, a solid, they don't dissolve. Magnesium hydroxide is a good example. Okay. Now, that aspect of it. Now, when we talk about solubility, we have to be very specific with temperature, because solubility is a function of temperature. We know, or maybe you don't, that if we want to get something in solution and it's not dissolving, what do? We heat it up. Okay. Cold iced tea, trying to get more sugar in there is kind of tough because it's cold and there's not a lot of room for more sugar into the iced tea solution. But you use warm tea, you're able to get more sugar in there, okay, because the solubility increases as you increase the temperature. So when we talk and deal about whether it's soluble or insoluble, we have to be very, very specific with temperature, and we talk about 25 degrees Celsius. That's our reference point. Obviously, if you're 100 degrees more material that's normally at 25 degrees is insoluble, but when you're at 100, it may go in solution. So, you know, we can't really compare apples to apples there, okay? So 25 degrees is our reference temperature, okay? So as I stated, soluble dissolves essentially completely, okay? 99.99% in solution. When it's classified as insoluble, it doesn't dissolve, but there's a small amount, a small percentage that does dissolve. So it still has electrolytes in solution. It still will conduct electricity, but not as well as a ionic compound is totally soluble, okay? Now, when we say it's insoluble, and then we designate it as a solid, its physical form is a solid. The other term too is when we talk about solubility, we use AQ. And so you may say, you know, for example, sodium chloride, and then in parentheses, lowercase AQ. What that is telling you is you have a aqueous solution of sodium chloride, okay? As compared to sodium chloride, to refresh your memory in the physical states, if we put an S, then it's solid. So that's basically taking the salt out of its container. It's solid. But the moment you put it in water, it goes in solution, and you make an aqueous solution, okay? All right, so let us go to the solubility table and how we use it to help us define whether an ionic compound is soluble or not in a water or aqueous solution. Note the table here is broken up into two columns. We have, let me change the color here. We have the soluble column, which is right here, okay, and the insoluble column, okay. So let us talk about the soluble column. Number one, when any anion, okay, I'm going to just designate it as A negative, some anion. Any anion that's out there, when it is partnered up with either lithium, sodium, potassium, or ammonia, okay, with these big four here, that ionic compound is always 100% soluble, okay? Always 100%. So anytime you see lithium, sodium, potassium, ammonium, and you need to determine whether it's soluble, you don't even have to use the table, because you know those four will always result in a soluble ionic compound. The acetate ion, which is one of the polyatomic ions found in the polyatomic ion table, it comes from acetic acid, which is vinegar, and that acetic acid has reacted with the base, acid-base reaction, remember, and the salt is called the acetate. Now, when the acetate anion, notice the anion because it's got a negative charge, is partnered up with any cation, regardless of what it is, okay? Copper acetate. Obviously, the number one, those four will always be soluble simply because of those four ions. But when that anion, the acetate, is partnered with anything else, magnesium acetate, copper acetate, lead acetate, et cetera, always 100% soluble, okay? Same is true for the anion, the nitrate ion. When it is bonded or partnered up with any cation, regardless of what it is, any positive charge metal, it is always 100% soluble. So you have, like I stated, copper acetate, I use that a lot, silver acetate or nitrate or anything, it will always be soluble. Okay, number four, the halides. Remember the chloride, the bromide, and the iodide. Okay. Normally, normally, and I take this, listen carefully, normally the chloride, the bromide, and the iodide, when it is bonded with any other metal, like the acetate and the nitrate, it is soluble, with the exception of three exceptions. Okay, and let me change the color here. And that is when the halide is bonded to silver, mercury, or lead. Okay, only those three metals. So if you got silver chloride or bromide or iodide, or mercury chloride, bromide or iodide, or lead chloride, bromide, or iodide, those individuals are insoluble in the precipitate forms. And we use that property, for example, if we ever need to determine, you're doing a water test and you need to determine if you have like chlorides or halides in your water, you put a little silver nitrate. Silver nitrate is insoluble because, again, number two, silver nitrate, always insoluble. But the moment I mix those together, if there's any chlorides or any halides in your water, it will combine and cause a precipitate and gets cloudy, because those three examples are, or any lead or any mercury in your water, it will cause a cloudy solution. Okay. All right. Number 5, the sulfate ion. Like the halides, like the chloride, nitrate, and the acetate, normally the sulfate ion is soluble whenever it is bonded to whichever metal. But there is 5 exceptions. When the sulfates are bonded to calcium, strontium, barium, silver, and lead, okay, 1, 2, 3, 4, 5, when those 5 metals are bonded to the sulfate, then it is classified as insoluble. Okay. And so you can have, a million sulfates, all soluble in water, except those 5. A million different sulfates, I should say. But it's exaggerating, but that's the point of any combination of sulfate and the halides normally are soluble, except those exceptions. You see? All right. Okay, so that's any questions about the soluble side. Okay, let me clear this up. That brings us to the soluble side, which brings us to the insoluble. Okay. Now, the thing about the insoluble is this. As I stated with number 1 on the soluble side, okay, any carbonate anion is normally classified as insoluble. So any copper carbonate, iron carbonate, any metal combination, normally it is insoluble and it causes a precipitate, except when that carbonate, that chromate, and that phosphate, that's 1, 2, and 3 on the insoluble column, except when those 3 anions are bonded to any of these 4 on number 1, then those guys are soluble, okay? Because always the number 1 over here, the lithium, sodium, potassium, and ammonium, whatever they're bonded to anion-wise, they're always soluble. So the chromates normally are insoluble, except if it's bonded to these 4. And the same is true for the chromate ion and the sulfate ion, okay? Now, with respect to the sulfide, remember the sulfide? Okay, again, the sulfides are insoluble unless it's bonded to the 4 and add 3 more. if the sulfide is bonded to calcium, strontium, or barium. So there are only 7 examples of soluble sulfides. All the other sulfides are classified as insoluble. See how that works? All right, and then finally, number 5, same thing, similar scenario. If the hydroxide is bonded to any of the 4 of number 1 on the soluble side, it is soluble. And then on top of that, there's 3 more. If it's calcium hydroxide, strontium hydroxide, and barium hydroxide, plus the 4. So there's only 7 soluble examples for the hydroxide, which is true for the sulfides. There are 7 soluble examples for the sulfide, okay? And then for the other ones, there's only 4, 4, and 4 soluble examples for each of the 1, 2, and 3, the carbonate, chromate, and phosphate. Everyone else is insoluble. Okay, so those big 4, the big 4, as I call them, lithium, sodium, and potassium and ammonium are always soluble, always soluble. And we can tap into this solubility properties, as I mentioned earlier, with respect to water. If your water has a lot of halides, we just hit a little silver nitrate in there. That silver nitrate is soluble, but when we add it with any water sample, like sodium chloride, then the silver and the chloride get together, and because of the nature of the bees, they're insoluble in water, it precipitates. And we can tap into that property here. And for example, in my previous life working with in industry, I worked with a lot of iron, okay? And I needed to find a way to get rid of iron and copper in the liquid that we were working with. So we would treat it with a hydroxide solution, like sodium hydroxide, and the iron and the copper would combine with hydroxide and form a precipitate. The result is we got rid of all those heavy metals and got them out, and our water was purified. We could dump that into the drain. And in fact, the water going out of our facility was actually cleaner with respect to metals than the water coming into the facility. But we were required by EPA to make sure that was taken care of. And we played with the solubility combinations as shown here. Okay. All right, any questions about this so far? How this table works? Okay. All right, so with that being said, then you may be given some examples here, like we have listed below, and try to determine whether this material is soluble or not. Okay, and so we look at what we've been given, and we have sodium sulfide. Well, off the top, right off in the beginning, you see sodium there. You don't have to go any further, right? Because you know that sodium bonded to anything is always 100% soluble. Okay, and so we can write the term, the physical state of AQ, meaning it is soluble in an aqueous solution. Okay. All right, let's take a look at the next one. So this is where we got to recognize we have the hydroxide here, okay? We know that because we've got parentheses. That tells us we're dealing with a polyatomic ion. We got the OH in the parentheses, so we go to the polyatomic ion table, look for the OH, and we find that it is the hydroxide polyatomic ion, which is number 5 here, okay? Now, normally, number 5 is in the insoluble table, unless it's bonded to the number 1 of the soluble table and strontium, barium, and calcium. That's not the case here because we see that it is bonded to aluminum. Aluminum is not part of the big 4, nor the other 3 examples in number 5, okay? So that tells you that aluminum hydroxide in a aqueous solution would be insoluble. And so we denote that by the letter S to tell you it's a solid. Keep it in mind that even though it's insoluble, if we needed to show this in a diagram, we have to show at least one pair of ions in solution, because there is a little bit still in solution, right? So if we were to show this demonstrate this in a diagram of a beaker, okay, of water, we would show the ion aluminum plus 3 hydroxides in solution. At least show one set, and then in the bottom it would show, we can write as aluminum hydroxide intact, okay, because they will precipitate, because it's insoluble. Okay, so the next one would be silver, which silver is we call those a heavy metal. Silver, mercury, and lead. Those are the bad metals out there, especially lead and mercury out in the environment. Okay, and so when you see that, you might think automatically insoluble, because in general they aren't, unless they are bonded to the 4 there. Okay, all right, but then you go over. Excuse me. Let me restate that. I meant to say bromide. Normally, the bromides are soluble, except when we're dealing with a heavy metal like silver, okay? So if we go to the halide ion, we see bromides in here. Normally, it's anything bonded to the bromide is soluble, except those 3. And one of them is those 3 heavy metals, is what I was trying to tell you. Those heavy metals, silver, mercury, and lead, when they're bonded to the halides, they're insoluble. Okay, so we designate that with the S. Okay. Now, this next one, all right, we got calcium, and then we got CO3, which is the polyatomic ion carbonate. So that brings us over here to the carbonate ion and the insoluble category. And so then we know it's insoluble unless it is bonded to any of the 4, which calcium is not part of the 4. So calcium carbonate is classified as insoluble, and therefore we designate the S. If you have ring around the tub, for an example, or around the spigot of your tub, there's some solid material hanging in there. That is calcium carbonate. There's a lot of carbonate and a lot of calcium in the water, especially if you've got heavy water. And that's what they mean heavy. We're looking for, there's a lot of ions in solution. And a lot of them, it's stated based on their property, are insoluble. Calcium carbonate is one that's insoluble. So you form a lot of solid material. All right, now the next one, pretty straightforward in this one. We got potassium nitrate. We got K up front, potassium. We don't have to go any further, right? Because we know automatically there's part of the big 4, lithium, sodium, potassium, and ammonium. The fact that you got potassium written there, just like the first one we did, sodium, don't go any further. You know that that thing is soluble, and therefore we can designate it as AQ. Okay. So that's how we utilize the solubility rules to determine whether a material is soluble or insoluble in water. Okay. Now, with respect to electrolytes, which is what I just mentioned, electrolytes are nothing more than these ions. Okay, so when we have strong electrolytes, okay, they are good conductors of electricity. And the reason they are good conductors of electricity is because these electrolytes are 100% soluble in water. Okay, and so the strong acids, strong bases, those guys 100% in solution. Plus these other ones like KBr, nitric acid, which is strong acid, potassium hydroxide, sodium chloride. Those ionic compounds, potassium hydroxide, sodium chloride, all are classified as soluble in water and therefore are very strong electrolytes and are good conductors of electricity. Okay. Now, with respect to non-electrolytes, these are these are covalent compounds. Recall the difference between an ionic and a covalent was the following. Ionic compounds, even though classified as soluble or insoluble, will go in solution. Some go 100%, some go much, much less, okay? But there's ions in solution. Covalent compounds, when they go in solution, are put in water, do not break apart, do not dissociate. The only exception was acids like nitric acid, hydrochloric acid, sulfuric acid, etc. Those are the only exceptions, and that's the nature of the beast for those acids, that they will break up into ions. But other than that, all other covalent compounds do not dissociate. So water, put in water, does not break up into oxygen and hydrogen, unless you put energy into the system. You can break up hydrogen you can break up water into hydrogen and oxygen, but you got to put a lot of energy into the system. Carbon monoxide, CO, and then C6H12O6. That's a organic compound. Okay, you may not know what it is, but if you look at it, you can see there's no metals involved. These are all covalent compounds. It's made up of nothing but carbon, hydrogen, and oxygen. That, by the way, is a general formula for sugar. These chemicals do not conduct electricity because they do not form ions. Okay, they are covalent compounds. They do not form ions in solution, and therefore no ions, no conduction of electricity. Okay. Now the weak electrolytes are those chemicals that we have defined as weak acids like acetic acid, or aka vinegar, or weak bases. Okay. And those, they will dissolve, but the majority of them are intact. Any of the insoluble ionic compounds are weak electrolytes, because even though they're classified as insoluble, there's still a little bit of ions in solution. So HF, a weak acid, magnesium hydroxide, classified as insoluble, silver chloride, classified as insoluble, and carbonic acid, H2CO3. Those are the weak acids we talked about previously. Okay. Weak electrolytes, there are poor conductors of electricity because they partially ionize in water. Okay. This summarizes them. Strong electrolytes, so all of the strong acids, all the strong bases, and any ionic compound that is classified as soluble, these are strong electrolytes. The weak electrolytes is the weak acids, the weak bases, and any ionic compound that has been classified as insoluble. Those are weak electrolytes. They have some ions in solution, but not a lot. And then the covalent compound, the non-electrolytes, those are any covalent compounds, with the exception of acids. Okay, and remember that, because acids will dissociate. Doesn't make them ionic. They form ions because they dissociate, but they're not ionic. Acids start off covalent and form ions. They don't start off as ionic compounds. Okay? But that means that all the other covalent compounds are non-electrolytes. All right, so if we look at these diagrams here, we can designate, if we had a beaker with a couple of electrodes, of positive and negative electrodes, okay? If we got electrolytes in here, you complete the circuit. The electrolytes, which are right here, think of them as the switch, the electrical switch on your light. When you flip that switch, you close the circuit and it forces electricity to run through your circuit, and therefore your lights light up. The electrolytes here act as the switch, and if they're capable of conducting electricity because of their charge, and then you're going to close the circuit. So that's what designated by that lightning rod there. Okay, so electrolytes will conduct electricity. Okay. If you have non-electrolytes, because there's no charges in here, like the covalent compounds, they will not close that circuit, and therefore you have no electricity running through that circuit. It will not conduct electricity. Okay. Electrolytes are, like I stated, very important, especially in your body. And they are crucial. The sodium ions crucial in muscle contraction, in your heart contraction, and there are so many things that go on electricity-wise in our body that without electrolytes, we couldn't function. Okay, so how do we designate diagrams to show whether it's a strong or a weak? Well, as follows: magnesium hydroxide, based on their solubility rules, shows it to be insoluble, so we got an S there. So we show the diagram here as follows. We got to show at least one set of ions in solution, okay? And the bulk of the other material is, down here at the bottom of the beaker, okay? Still intact, all right? And so that would be an example of a weak electrolyte. Now, CH4, the fact that you may not know what that is, that's okay, but I hope you recognize that this is a formula of a chemical, obviously, and it's made up of nothing but carbon and hydrogen, which then you hopefully should deduce that that is a covalent compound, okay? Let me restate that. You may not know what the chemical is, and that's quite okay, but I want you to recognize that this formula, CH4, is made up of nothing but non-metals, carbon and hydrogen. Therefore, you deduce that this must be a covalent compound, okay? So being a covalent compound, it's not going to dissociate. So if we were to put and bubble it through water, they would still be intact with no charges. Okay, so this would be an example of a non-electrolyte. And then finally, KCl, the fact that the solubility rules state that any potassium, I had calcium in my head, any potassium of the big four, remember the four, always soluble. So we show that by writing, at least 3 or 4 pairs of these ions in solution. So notice when you do write them out, that you make sure you got the same number of positives and the same number of negatives. You got 4 positives and 4 negatives, okay? And so they're totally dissociated, totally 100% separated. It would be incorrect to show it with potassium chloride intact, because potassium chloride, and sodium is soluble. Okay. All right, so, let me clean up my mess here, hold on. All right, so, let me reemphasize here. So this would be a strong electrolyte. This would be a non-electrolyte, and this one would be, the magnesium hydroxide would be a weak electrolyte, okay? All right, so you may be given a list, and then you're asked to classify whether they are a strong, a weak, or a non-electrolyte. Well, in order to do that, you're going to need the solubility rules with you first, okay? You can go through the list very quickly and separate the ionic and the covalent. But let's go through. Let me give you why. Here's the answer, and we'll talk through why that's the answer. Okay. Number one, barium sulfide. Okay. It is classified as a strong electrolyte because it is soluble. Okay. It is soluble in an aqueous solution based on the solubility rules. Okay, so it's a strong electrolyte. Silver chloride. So you look at the chlorides, the halogens. Normally the halogens are soluble unless they're bonded with the heavy metals. One of them is silver. That makes it insoluble. Okay, so silver chloride is classified as being insoluble, that being an S. Therefore, it makes it into a weak electrolyte. Okay. Number three, you got K right up front, potassium. Don't have to go any further. You got potassium sitting there. Okay, that automatically tells you I got a soluble solution, regardless of what follows, because I simply got potassium as part of those four in number one, the first column. Okay, that makes it a strong electrolyte, the fact that it's soluble. All right, H2CO3, hopefully you recognize that this is an acid, and it's one of the weak acids we gave you. HF was another one, gave you some other ones there. So this is a weak acid. It means it will dissociate, but not very much, okay? And so that makes it a weak electrolyte. Carbon dioxide. This is a covalent compound, right? Nothing else bonded there. It's a covalent compound. The fact that it's covalent, it's a non-electrolyte, okay? Now, number four, you might ask, well, wait a minute. Number four is also covalent. But again, remember, normally hydrogen's written up front, like H2 would give you a hint to tell you I'm dealing with an acid. Okay, so that gives you opportunity to go look that up. Which one am I dealing with? Well, I've got the CO3 after all that, which comes from the carbonate, the CO3 -2. So this carbonic acid was reacted with the base to get rid of the two hydrogens to give you the carbonate ion. So those two hydrogens up front should flag to you, oh, I got an acid here, okay? And it happens to be a weak acid. All right, number six, like number three, it's sodium. Sodium automatically is part of the big four there, the top four, lithium, sodium, potassium, and ammonium. So you don't have to go any further because you know that it is a soluble, okay? And the fact that it has the hydroxide polyatomic ion, remember the definition of a base is Arrhenius base is any chemical when put in solution produces a hydroxide ion. So this is a strong base because it produces the hydroxide ion plus sodium makes it soluble. So it's a very strong electrolyte, okay? Calcium carbonate. Well, we look up the solubility rules for carbonates and we see that it is classified as insoluble based on the solubility of the carbonates. Okay, so being insoluble makes it a weak electrolyte. Number 8, again, we may not know what it is specifically. This is a general formula, but we do know that we have nothing but carbon, hydrogen, and oxygen, which makes it a covalent compound. Okay, this, by the way, is sucrose, for general formula for sucrose. Being covalent, it will not conduct electricity. Okay. And then number 9, right up top, you got sodium up front. Don't have to go any further, okay? Because you know, anything following that makes no difference. The fact we've got sodium to begin with tells me it is soluble. Being soluble tells me I have a strong electrolyte. Okay. And then the last, lead is a good hint. We're talking about the heavy metals. Remember the heavy metals, silver, mercury, lead. Those are the heavy, nasty metals. Normally they are insoluble, so that sends you off to search and find out. The sulfates are, a lot of sulfates are soluble except when they're bonded to the heavy metal. That makes them insoluble, a solid, therefore a weak electrolyte. Okay? So a systematic approach to each one, determine what it is. Okay? You got barium sulfide, so that's ionic compound. So we're going to deal with solubility. So you go to the solubility rules, determine whether barium sulfate is soluble or insoluble, which then tells you whether it's a strong or weak electrolyte. Okay. If it's a covalent compound, okay, first determine, like these number 4 and number 5, that number 5, obviously it's not an acid. Number 5 is not an acid for one. There's no hydrogen in number 5, carbon dioxide. So the fact that it's covalent and there's no hydrogen involved anywhere in the formula, covalent, non-electrolyte. The thing about when hydrogen is involved, normally it is hydrogens are written up front first, okay? And that's a good indication that you might be dealing with an acid, all right? And then from that being the case, notice when I write H2SO4, okay? I got the hydrogens written first, HCl, okay? HNO3. You got hydrogens written first. So it's a good flag to tell you I might be dealing with an acid, and then go determine whether it's a strong or a weak acid. Once you determine that, in this case, this was a weak acid, we have a weak electrolyte. Okay. Any questions right here about the solubility? Okay, good. Because guess what? You are done with chapter 9. Okay. All right. Any questions? I was thinking about continuing with chapter 10, but I'll leave it up to you. I can wait till you guys get back from coming back from Cancun. Or I can get you to start it now. We can stop it here and then you can start your break. Or we can continue. How many want to continue into chapter 10? You can type in your chat. You see, there's 1, 2, 3, 4, 5, 6, 7, 8 of you. If I get 5 yeses, then I'll continue. It's about 50%. You want no, you can type no. If I get 8 no's, then obviously that's the answer. But if I get 5 no's, then we'll stop here and continue when you get back.
No.
Okay, that's a 1 no. If there's no more no's, I have to infer that it must mean yes.
I would rather.
Does not divide evenly.
Okay, you rather not? Okay, that's 2.
I would rather not.
Okay, that's 3.
Doesn't matter.
Okay, got a neutral. Okay, so why don't we just stop it here? Okay, and start fresh on chapter 10 when you get back on Tuesday. Also, I will also be open to any questions that you may have on Tuesday with respect to chapter 7, 8, 9. So if you want to